Good morning, everyone. Welcome to the EasyPower Thursday webinar. My name is Jim Chastain. I'm Applications Engineer here at EasyPower. And we've selected this topic because recently we've had, more inquiries and more hits, if you will, on the website regarding this topic. So welcome to the presentation. Here's what our agenda looks like for today. We're going to start with a couple poll questions and talk a little bit in terms of the definition of terms and, at least in my opinion, how there's some room for confusion when we're talking about different aspects of power systems. Then focus primarily on fault current analysis, where the data is generated, displayed, and can be either reported or utilized in the calculations. And hopefully that covers. Now, this is not meant to be an exhaustive discussion of, if you will, the specifics of symmetrical and asymmetrical arcing current or fault current, but more towards how to utilize the tools to extract that information from your system. So welcome, and let's jump into it. So now our first poll question is basically to get some feedback on how often you get requests from your customer base to discuss or report Thevenin equivalence. And I know it's something that it's not something I do often, but it comes up from time to time. And I just want to make sure that people are aware that it's a function or a feature in the EasyPower tools. And so we're going to touch on it briefly. Okay, so it looks like we have a quorum. Here's how people responded. As I expected, it's not something that's an everyday occurrence, but it's out there. And then secondarily, how often in your experience does a project require coordination of ground fault devices? And this one I expect to be a little bit more active, especially in this area that we're discussing today. Do appreciate your support of EasyPower and your attending the webinars. I would encourage you from time to time to check out the newsletter to get updates on the webinars that we have upcoming. We actually have some fairly interesting topics that will be included in the next couple months. So looks like we have a quorum here. Here's how people have weighed in on this. And that's good to know that we're aiming at the right place for the discussion. So let's mosey. So as I mentioned earlier, in general, they're fairly simple definitions. Symmetric refers to something that's usually balanced, or in many cases a mirror image in terms of the waveform, and the balance is usually around some reference point, and usually in waveform parlance that's the zero axis in the amplitude. Asymmetrical then by default is anything that's not balanced. Now, the reason that I think, or at least in my opinion, there's some potential room for confusion is that these terms are applied in different areas, not just in the fault current. And so specifically, there are four types of faults. First of which is a balanced three-phase fault, and by definition, all phase currents are equal in magnitude, and so again, it would be referred to as a symmetric fault. Three phases are bolted together because it represents a worst-case fault any system will see, and it's also the basis for the arc flash calculations that's reflected in IEEE 1584. And consequently, they only use the three-phase balance fault because it is the worst case. Now, unbalanced faults, characteristic would be a single line to ground which the phase currents are not equal, and again it's considered an asymmetric fault. EasyPower will show these results, but again it won't be used in calculating arc flash. Another asymmetric fault, or two others, would be line-to-line faults and then dual line to ground. And as we'll see, the phase currents are not equal. And I don't mean to overemphasize this in this particular case, but virtually in every case when we're talking about bus currents, the summation at the bus will be a vector sum of the currents involved. And for some reason, typically, at least in my demonstrations, we typically show magnitude, and frequently that won't always be the total of the currents being analyzed. So let me jump into EasyPower real quick and kind of show where these faults show up. So here's a typical one-line diagram, and when we go into short circuit focus, we're looking at the second line of the ribbon up here, the types of faults that we're generating. So if we fault all the buses, we're looking at the A phase and a three-phase balance fault. And it behooves us to look at just a single phase because by definition everything is equal and there's no need for the redundancy. So this again is the only balance fault that is used for arc flash calculations. Line to ground fault then, on the other hand, will show in the three phases different fault currents. In this case, the high current phase will be that which is grounded, and the other two will show relatively low current because of the zero voltage on the bus. And for those of you that don't use the tool that often, what we're displaying is a single bus fault. In this case, I've just highlighted bus 2, and so it's the faulted bus, and all this other data that we're showing would be considered remote current, and this is all a function of the way short circuit options allows us to display the one-line output. So in this case, we're showing symmetric current, we're showing remote bus faults, and magnitude only. And then another asymmetric fault would be a double line to ground. And again, the two high current phases would be the ones that are located or that are faulted to ground into each other. The significance here is that when we look at the grounded part of the system, sure enough, we have relatively high current in the two phases. And if we look at the ungrounded part of the system, we have an imbalance in the phases because the shorted phase will have the higher results, and then the ground current is effectively not going to show up as a standalone phase. And then finally, line to line, where we have no ground interaction, so we only see the two phases between, in this case, B and C. Now, it's worthy of note. What we're showing here is the current in line and then the per unit voltage on the bus itself. And so this is the voltage on phase A, but since the fault is between the other two phases, they will be at reduced voltage. And consequently, there's no current on phase A. Now, if that's too much information, we can always reduce the display of the remote buses. Now, so those are the application of the short circuit currents on symmetrical and asymmetrical faults themselves. Now, the next type of application of these terms is what's referred to as symmetrical component method, and this is a method of systems analysis that's extremely useful for unbalanced faults. And basically it's a conversion of the unbalanced system into a balanced representation, which is easier to analyze, especially with multi-phase systems. And so this, even though it's a technique that was developed 100 years ago, it's still useful today, especially in the age of computers where we have more analytical capability. but it gives us a very convenient way to analyze unbalanced systems or non-balanced systems. It's most often applicable in ground fault analysis, transmission line applications, and transformers. We have a very excellent video on this on the website, and for a much more extensive discussion of the applications and the derivation, I would refer you to this on the EasyPower website. Just look up symmetrical component video, and you'll find a very excellent discussion. But basically, when we're talking about symmetrical components, the system develops a positive sequence, which is referenced to the normal phase order A, B, C, and then a negative sequence, which refers to the reverse order, which would be an A, C, B, and then the third element, the third symmetrical component, is the zero sequence, and there we only see evidence of that being included when we have ground current. And so that's why this particular application is extremely useful in ground current applications and transmission lines where you're worried about ground faults. Now how this appears in EasyPower, if I go back to my display of a balanced three-phase fault, on the top row I have plus, negative, and theta. The plus sign gives me the positive sequence value of a three-phase balanced fault. And if we look at the negative sequence, we see that there's zero involvement. And if we look at the zero sequence, there's zero involvement. So again, this is a different representation, and it's specifically referring to the sequential method or sequential component method. If we look at imbalanced faults, we'll see that on the positive, negative, and zero sequence, we have different values for each of these, and because this is a line to ground fault, we see fairly significant current in the zero sequence, and again, it doesn't show up in the ungrounded part of our system. So this again will be an important part of the analysis and the calculations. Additionally, in the line-to-line fault, back on the positive, negative, and zero sequence, we can see there is an involvement in the zero sequence for the line-to-line. In this case, it's line-to-line to ground, double line to ground. And so the ground sequence, the ground fault current will be the zero sequence. If we go just to a line-to-line, then the zero sequence again is taken to zero. So again, I recommend you refer to that explanation and very useful discussion of the application of zero sequence process or methodology in ground fault analysis. Now, again, that's not where I wanted to spend the time, so I'm just passing over these or mentioning these in passing. And it brings us back to the basic three-phase alternating current discussion, which is where we titled this symmetric and asymmetric fault currents. Anytime we're looking at an electrical system, there's basically two currents that we're concerned about. The first is load current, which is normal operations in quiescent and steady state. And there are times that we want to look at transient response and harmonic response of these considerations. And three-phase analysis is useful. Less concern about imbalanced loads because it goes to the discussion about capacity, and it's not the maximum stress on the system. It ends up being more a nuance in the steady state, or influences or effect on the steady state, which could be affected by the different phase currents. The other type of consideration we look at when we do a new design is a short circuit current. And the problem there is this is uncontrolled flow, and our main focus is to make sure that the system will survive the worst case and, if at all possible, be able to protect itself. And that worst case, frankly, is in when all three phases are bolted together as far as the short circuit current. So in terms of short circuit current, symmetry is defined as the point when all the AC positive and negative peaks are symmetrical around the zero axis. And at that point, it's called, and again, this is what we will get in a three-phase bolted fault. On the other hand, when these positive and negative peaks are offset or centered somewhere above or below the zero axis, then this current is considered asymmetrical. And it comes into play because we have to ensure that our ratings on our different protective devices can deal with these peak currents and operate properly. Now, over time, and when we say over time, we're talking about a number of cycles, the fault current has two elements, and both may decay over time based upon the changes in the system during the fault. When we look at the fault being generated, or the fault as affecting the utility supply or the power supply of an AC system, it looks something like the waveform here in the center, where even though it diminishes because of changes in the system, it still is symmetric in that it's balanced around the zero axis. The waveform is balanced. Now, at the same time, depending upon the fault origination and some of the other factors in the system itself, there will be a DC offset introduced at the time of the fault, at the location of the fault, and this causes a DC component, again, usually short-lived, anywhere from 10 to 30 cycles of a decaying DC component. And as that's applied in the fault itself, we get what's referred to as an asymmetric waveform, and that's because it's the total sum of the DC and the AC components. So the question is, what's happening and where is this coming from? Well, it takes us even a step back to a basic electrical analysis, which is, if you recall, the mind crutch Eli the Iceman, which reminded us that the current lags voltage in an inductive system, and conversely, the voltage lags the current in a capacitive system. So if we look at the waveform in a purely inductive system, the current itself will be offset by 90 degrees and delayed compared to the voltage waveform. Now, most industrial systems have a lot of inductance and some amount of DC resistance in the form of a cable impedance and the like. And so very seldom do you find a purely inductive system in real life. And so there's a measure or a comparison of the inductance, inductive reactance compared to the DC resistance, and we refer to that ratio as X over R. And so X represents the inductive reactance or the system reactance at 60 hertz, and the R represents the DC resistance. And so it's this comparison, and the unit circle is basically the starting point for this discussion in polar coordinates. The resistance will be, in this case, along the horizontal axis, and the reactance will be in the vertical axis, and it's that ratio that we refer to X over R, and it's that angle or that phase of that angle that gives us power factor. So it can't be overstated how important this term X over R is, because the higher the X over R, the slower the DC decay. And in most cases, most applications, small motors, their contribution current, which is affected by this DC offset, lasts no more than 3 to 5 cycles, whereas large motors generally will last anywhere up to 100 to 30 cycles, but generally you see them gone by 30 cycles. Now, why do we care about all this? Well, again, this is the worst case situation that the system will ever see, and for it to be able to withstand this surge or these peaks of current, we need to comprehend this factor into our design and selection of protective devices. And so since they need to survive the worst case, we need to make sure we're talking apples and apples when it comes to the way they've been tested in the factory compared to the way they're going to be applied in our application. So because the actual current can vary widely, and when we mean this, the DC offset is going to be different virtually every time we have a fault or every time we have an interruption in the current, and that is based upon the waveform, the voltage waveform, and at the time and that phase that that the fault occurs. So when the voltage is at 0 is when we have the maximum current, and depending upon whether it's going negative or going positive on the waveform will determine which direction polarity-wise the offset is affected. And usually, because we have a 3-phase system, all separated by 120 degrees, there usually is at least one of the phases that's near its peak contribution point, whereas the other two may be less so. So circuit breakers are tested using power sources with an X over R, I meant to say ratio, as prescribed by industry standards. So they could be an irration, and that is, again, there's a need to have everybody on the same page. So, yeah. So for the high voltage breakers, we see ANSI standard IEEE C37.10, and for low voltage breakers, it's C37.13. And I think on my handout section of this webinar, I have two documents, one of which is additional reading if you want an in-depth discussion of the applications of these parameters. I would strongly recommend that you look at some of these books available in the market. Conrad St. Pierre, Jim Phillips, and then a grounding book, but these get into very comprehensive discussions and for the most part describe exactly how EasyPower is applying these principles. And then the second handout is a discussion of the standards and applications that EasyPower utilizes to do the calculations that we have in the tools themselves. And it boils down to, and in fact, I think these may even have been updated more recent than these dates. But the bottom line is industry has agreed upon the environment that they test the breakers, the protective devices, and along with their data sheet, they will describe the standard that they're adhering to, which gives us, the users, the X over R reference point, and any place in our system that point may be, that X over R value may be different. So when we get into the software itself, EasyPower actually calculates the X over R at every bus. And once we have identified the protective device that's being utilized on that particular bus, then the data sheet information from the manufacturer is used as the reference point, and we compensate for the difference in what's being measured versus how the device is being applied in the system. The analysis is being applied in our one-line diagram. And just a side note, as you can imagine, this is fairly heavy-duty computation load. And when you calculate X over R at literally every bus in the system, and because it's all interactive at each fault, there's some need to be fairly rigorous. And that's one of the things that sets aside, if you will, less costly analytical software, is because they handle this discussion only at one data point for utility. So all these measurements are being made from the point of the fault back to the source of the energy, the source of the power. And in most cases, that is primarily a utility. And as I mentioned, some pieces of software only deal with an infinite source, and consequently there's some reason for I guess inadequacy or differences between the comparisons that are being made. All right, so then let's jump into where EasyPower actually uses this. So we develop the parameters of symmetrical and asymmetrical current in short circuit, and we can show it both on the one line and in the reports. And then when we're doing a coordination in plotting the TCC curves and the one lines. And then this information is available and can be controlled as far as some of the application in the device library, and the way that the X over R calculations are being made themselves. And so give me a couple minutes and we'll kind of illustrate that on the EasyPower application. So I really do want to jump out of here and go to a little bit more complex system. Now what we're going to be showing is, so what we're talking about is in short circuit, the ability to display asymmetric faults. And so we've already discussed that the three-phase faults is a balanced fault. And to see a difference in the different current, we would be talking about an asymmetric fault. When we calculate or we fault all the buses in a three-phase balanced fault, again, I'm looking only at the A phase, and we're talking about, let's fault everything. The contribution current, in this case, will be coming 9,300 amps from upstream, 600 amps, 5 amps, and 148 amps. And again, this is a case where this particular totalized short circuit current may not equal the sum total of each of these devices, each of these currents. The reason for that, if I go into short circuit options, I can control what's displayed on my one line. So on the one line output, we're showing symmetrical current, and right now we're only showing magnitude of the coordinates. If we look at this and display the magnitude and angle, we can see that we will get an accurate representation or an accurate vector sum of the different currents coming into this particular fault. Now, if we come back to our short circuit options, if we want to look at asymmetric, we can do the same by selecting the display to be in asymmetric terms. And again, we're showing only the asymmetric faults, asymmetric magnitude. And on the remote bus voltage, we're seeing per unit values. So and this is for a single bus fault. So let me kind of briefly talk about that. If we fault just this one bus, then this gives us our total current on the oblique. We see the total magnitude. Again, we're showing asymmetric. on a remote bus, we're showing the branch currents, but on the oblique here, we're showing the per unit value of the voltage itself. And if I come back to my short circuit options, that per unit value can be shown in kilovolts on the remote bus. All right, so that's asymmetric. Now, and finally, if we want to show the combination of asymmetric and symmetric, or the comparison, we can show max asymmetric and max symmetric. And as we do that, we get two values, one being, and we're looking at the half cycle point, symmetric will be 10,000 amps, asymmetric will be 15,000. Now, if we look at 5 cycles into it, we'd expect to see a lower value for the asymmetric current, and then they should be equal at the 30 cycle point, which we in fact do see. Now we can't show all three of them when we're showing the display. But if we come back to short circuit current and show just asymmetric, we can see that decline over time. Okay, so that's fault currents on the one line. Now, this still pertains to the unbalanced faults, and in the case of faults that include the ground current, there's a lot of information to be displayed, both in symmetric and asymmetric, but it's not used. The only reason it's not used is it's not the worst case for the system phase fault. Okay, I wanted to show this is on the one line. If we pick out a selection and produce a report, under the reports, we can show high voltage and low voltage momentary report. We can include the duties and apply it. And as we do, we see a single phase fault with the X over R calculation, and then all the remote voltages and current for each of the phases. If we go back and have a multi-bus fault, we see both high voltage and I guess I want to make sure I fault all of them. Now here again, I'm reemphasizing the point that the tool is calculating the X over R at each bus, and this gives us the ability to then comply with, or at least have a comparison between the asymmetric and the 2.6 times the symmetric value that's prescribed by the standards, and how that compares to what the manufacturer has provided on the data sheet. And likewise on the low voltage momentary, where the equipment duty amps, that has to be compared against the manufacturer's data sheet, is calculated based upon the type of standard. Now I didn't kind of go into that. Let me do so. If I want to go back to my, I'm going to take off my short circuit spreadsheet. If I go back to the database edit and look at a protective device, say this high voltage breaker, what we see is that the manufacturer has, under the short circuit focus, has given us a reference that they are testing to an ANSI symmetrical standard, and these are the ratings that have been listed on the data sheet. And these will be pulled up as I make the part selection and then calculate to pull the part number out of the device library. So for every manufacturer's part number that we put together, if you click calculate, it'll pull these numbers up, and these will be used for comparison against the fault current that's being calculated. Now, one other point that comes up, and this is something that is probably pretty useful to people that get into the details of fault current analysis. We go into our short circuit focus and our control system for short circuits. We actually have the ability to calculate X over R with different methods. By default, we use the ANSI standard, but if necessary, it's also the ability to choose standard, complex, and characteristic current calculation method. These are described when I go to the help structure or help system with the X over R calculation described right here. I don't have a clue where I would apply one or the other, but it's described in this particular reference. Now, to show how that impacts the calculations, let's kind of go back and let's say the 5 cycle, let's calculate the results here and look at my short circuit current. So let's take a copy of this. To save it for posterity or comparison. And then go back and fault that same case with a different comparison calculation method. So let's use the characteristic current and apply it. And then as we look at that, we should see a different value for X over R. So let me come back here and compare this. And I don't see a difference. Let me see if I did that correct. Yeah, so we'll get different values for, I'm showing PSC rather than just the one. So let me close this and go try it again. I want a intermediate current. I want to fault the buses. I want to look at my short circuit reports, and this is in the characteristic. Let's see if I got this right. Still getting 7.9. I got to check my notes on that one. Point being, the X over R will be recalculated based upon the different method used, and it's that that value that can impact the fault current symmetric contribution during a fault. Now the other place that this will show up is in coordination. And so if we go into the coordination module and we plot some of these devices, we can see the effect of the different calculations of short circuit current. I guess I need to have a bus here. So I want to fault the bus downstream. And as I fault this particular bus, we have tick marks that show up on our TCC curve. And in general, the TCC is giving us the asymmetric current. So if I'm faulting refiner bus, it'll show me the asymmetric current through R8 and R30. And at the same time, I can control the TCC plot, it's TCC1 line, to show the asymmetric current or the symmetrical current. And we get different values based upon what's being displayed. Now, relays themselves will show whatever the relay setting is. Normally, relays work with symmetrical current, and so this is not that good of an example as it would be if I were picked out a breaker. So let's go back and make the comparison with breakers. So what I'm trying to show here is if I fault this particular bus, these tick marks that are showing up are in asymmetric form as opposed to the current that I'm seeing on the one line, which generally is in symmetric form. And I can change those with my TCC options. So here we got 14K coming up through BL3, and BL3 is 15.8 on the TCC curve. So this is asymmetric, and if I change my TCC, again, there's a lot of questions come up because we're showing a different value there. If we apply the asymmetric value, we'll get the 15.895 that is identifies with what's being displayed on the TCC plot. Okay, so the things we've emphasized is where the different currents can be displayed. It will change at the point of calculation based upon the DC contribution for that fault. For instance, half cycle versus 5 cycle, you should see less asymmetric current. It can be displayed usually on the TCC one line and on the TCC itself based upon the options I've selected. And likewise in short circuit current, we have the ability to change the way the calculations are being made for X over R, all of which affect our short circuit analysis and ratings or comparison ratings on the breakers themselves. Okay, I think that covers most of what I was trying to deal with here on our agenda. Basically, we discussed symmetric and asymmetric currents, the factors affecting how they're calculated and extracted from the one line, how they're being applied per the ANSI IEEE standards, and how important X over R is, and conversely or inversely, how important the values of the utility interface is, because that's the reference point that we have for all of these calculations. And we showed how the one line displays and the symmetrical and asymmetrical values are displayed in the reports. So let me see if we've got questions now that we can address. And my apologies if we went through any of that too fast, but it was, we got a couple of questions. Let me see if I can pull them out. Can EasyPower model unbalanced conditions, for example, opening one of 3 phase systems, or is it also unbalanced? So the answer is no as far as opening one of the phases. That's something we should have out literally within a few months as far as a single phase solver. The current version includes the ability to do unbalanced analysis in terms of just the fault itself, but it's not used for arc flash calculations. So what's the threshold between small and large motor? That's actually a good question, and it really ends up being on the system. In terms of arc flash contributions, where the IEEE standard recommends that we include any contribution for motors over horsepower or 37 kilowatts. In those cases, it's possible to group motors, lump motors. So if we had a dozen 10 horsepower motors, we could group that as, if we had a group of 10 horsepower motors, we could lump that as 100 horsepower, but have a smaller X over R contribution? So the answer is yes. If my system has a 500 horse motor hanging on a 4,000 volt bus, that's going to have a lot more import in the X over R calculation than a 10 horsepower motor hanging down on a 480 volt. So it's worth, and it's one of the high values of EasyPower, where it's just as easy to do a what if and see how that affects your results rather than stay with any particular dictate. Only infinite source when calculating the X over R. Okay, so maybe I didn't cover that. It's I've heard it discussed in different periodicals that some analytical software can do short circuit analysis only by using an infinite source. I just wanted to emphasize that that's one of the strengths of the EasyPower tool suite, is that you can use an infinite source just as a starting point, but in reality, you want as accurate a report on your utility source information, both in impedance and in short circuit current, because that will be taken into account when we're calculating X over R within the system. Okay, thank you everyone for attending, and by all means, visit the website, check out the newsletter, and we'll be talking to you down the road. Have a good day.